Large reasoning models, or LRMs, represent a significant advancement in artificial intelligence, particularly in tasks requiring deep logical thinking, such as mathematics, coding, and problem-solving. This survey paper titled Safety in Large Reasoning Models, a survey, authored by Cheng Wang, Yu Lu, Baolong Bai, Dujun Zhang, Zhongzi Li, and Zhengfeng Fang from the National University of Singapore and the University of Chinese Academy of Sciences, provides a comprehensive overview of the safety challenges associated with these models. At its core, the paper highlights how LRMs build upon large language models, or LLMs, by enhancing their reasoning capabilities. These models excel in deriving conclusions through step-by-step processes, thanks to techniques like chain-of-thought prompting, which encourages models to articulate their reasoning clearly. Other methods include self-critique, where the model reviews its own outputs, plan-and-solve approaches that break down complex problems into sub-goals, debate protocols involving multiple agents to reach consensus, and structural transformations like tree-based deliberations or dynamic tables for better transparency. The paper points out that recent developments, such as OpenAI's O1 series and models like DeepSeek R1, KIMI 1.5, and QWQ, have been trained using reinforcement learning to produce detailed, human-readable reasoning traces. This makes them highly effective in areas like mathematical problem-solving, closed-book question answering, and code generation. However, as these models integrate into high-stakes applications, such as scientific research or autonomous decision-making, their safety becomes a critical concern. The authors argue that while there are existing surveys on LLM safety, LRMs introduce unique risks due to their advanced reasoning features. The survey is structured to first provide background on LRMs, then explore safety risks, vulnerabilities to attacks, defense strategies, and finally, future research directions. In the background section, the paper delves into the roots of LRMs in reinforcement learning, where models learn through interactions and rewards to optimize decision-making. It references foundational work like AlphaGo and AlphaZero, which demonstrated how combining reinforcement learning with deep neural networks can handle complex, unstructured data. More recently, techniques like reinforced fine-tuning have been used to refine LRMs, allowing them to improve their deduction processes over time. Moving to safety risks, the paper examines how LRMs can falter in various scenarios. These include potential failures in logical consistency, where models might generate plausible but incorrect conclusions, biases amplified through reasoning chains, and issues in real-world deployment, such as misinterpreting ambiguous inputs or cascading errors in multi-step processes. The authors categorize these risks based on factors like the model's training data, prompting methods, and interaction with users, emphasizing how reasoning enhancements can inadvertently introduce new vulnerabilities. The survey then addresses adversarial attacks on LRMs. These attacks exploit the model's reasoning capabilities to manipulate outputs. The paper categorizes them by objectives, such as evasion attacks that trick the model into producing harmful or incorrect results, poisoning attacks that corrupt training data to bias reasoning, and extraction attacks that reveal sensitive information through crafted queries. For instance, attackers might use subtle prompt engineering to bypass safety guards, leading to unethical advice or fabricated data in domains like healthcare or finance. To counter these threats, the paper discusses various defense strategies. These include robust training methods, such as adversarial training, where models are exposed to potential attacks during development to build resilience. Other approaches involve input sanitization to filter malicious prompts, output monitoring to detect anomalous reasoning, and alignment techniques that ensure models adhere to ethical guidelines. The authors also highlight the role of interpretability tools, which make the model's step-by-step reasoning more transparent, allowing for easier auditing and correction. Finally, the paper outlines promising future research directions. It suggests focusing on developing standardized benchmarks for LRM safety, integrating multimodal reasoning to handle diverse data types, and exploring hybrid defenses that combine human oversight with automated systems. Additionally, there's an emphasis on ethical considerations, such as ensuring fairness across cultures and mitigating long-term risks as LRMs evolve. Throughout the paper, Figures like a timeline of LRM developments and a structural overview of the survey help visualize the progression and organization of these topics. Overall, this work aims to provide a structured understanding of LRM safety, paving the way for more secure and reliable AI systems.